back for the last topic of this unit, most likely, inverse functions. Okay, so today our goal is going to be to find inverses, whatever those are, verify them, and especially with nonlinear functions, and hopefully solve maybe a real-life problem that involves inverse functions. Definitely those first two things. All right, so first off, let's take a look. I'm going to zoom in a little bit. Let's take a look at two functions. So we have this equation, y equals 2x plus 3, where we're multiplying by 2 and then adding 3. That's the order of our operations. And then we have this other function where we are subtracting 3 and then dividing by 2. Okay, now I want you to notice that addition and subtraction, they undo one another. I'm going to write that word down. Undo each other. And then multiplication and division, they also undo each other. That's because that's the key thing you need to know about inverse functions. Inverse functions are pairs of functions or operations that, here I'm going to write this right down here, undo. Okay, think about the fact that in math, whatever you do, whatever operation you do, you can also undo it, okay? Meaning you can like kind of reverse it, okay? Like reverse that happening. It's like walking forward and then walking backward, right? Or spinning one direction and then spinning the other. So again, that word, undo, that's going to be a big focus today. So the official thing that we're saying is that functions that undo each other are called inverse functions. Okay, so they're like pairs of things. One function generally has an inverse. So the original function would be 2x plus 3. And so this is the original, this is the inverse, right? As I've got it written right here. But this is your inverse, okay? And if you'll notice, we're dividing by 2 instead of multiplying by 2. We are subtracting 3 instead of adding 3. So everything is inverse. Now, because inverse functions interchange the input and output, the domain and range also change. So here's maybe the note to make. With inverse functions, inputs and outputs switch. So basically x becomes y and like y becomes x. So since the domain is all of our x values and the range is all of our y values, those switch as well. So if you look at these two tables I have, the x values became my y values, just as a small sampling, and the y values become my x values, okay? So those switch. What that looks like visually in the graph is that you will see, if you were to graph a function with its inverse, you will see a type of symmetry where there's a reflection along the y equals x line. And that's because if you take any point along the function, so here's my function, I've got a point at 1, 5, that point gets transformed as it gets switched to the inverse to 5, 1, okay? So it's not quite symmetric because it's not one function symmetry, it's a pair of functions, but that's what they appear like when you look at them visually, okay? So now, this whole switching idea, the domain switching with the range, using the inverse operation, right, switching with which operation, all of this leads that to, okay, this is all great that I was given an inverse function already, but how do I find it? So to find the inverse of a function algebraically, what you're going to do is you're going to switch the roles of x and y, like in the original function, whatever you were given, and then you're going to solve that new thing you wrote for the output, and that will help you create your input. So once you've solved, you're going to have the inverse, which we would note if the original The original is f of x. The inverse is f negative 1 of x, meaning f inverse of x. All right, so let's try that right now. So this is my function f of x. So our goal is to find f inverse of x. So the first step, step 1. Now, I said switch the roles of x and y. Keep in mind that really this is y equals a third of x minus 2, right? Because f of x is our output. So we're going to switch the x with the y. So I'm going to have x equals a third of y minus 2. That's our first step. We're going to rewrite this. Basically, this one as x equals. And then step 2 is we're going to solve. So we're going to take x equals a third of y minus 2, and I'm going to solve it for y. I want to get y by itself. So the first thing I need to do is add 2. So I get x plus 2 equals a third of y. And then if I have a third of y, I can multiply that by 3. So I'm going to multiply the other side by 3. So a third times 3 is just 1. So I have y is equal to 3x plus 6 when I distribute. Okay? So my answer to what is the inverse is that f inverse of x is 3x plus 6. Now, sometimes it'll be a little bit easier to see than others, but if you'll notice, we are multiplying by a whole number instead of a fraction, and we are adding instead of subtracting. All right, a couple more examples for us. So I've got 3 different situations. I've got a quadratic, a cubic, and a radical. Still the same basic process. Switch x and y, and keep in mind y is often written as f of x. Then solve. All right? So I'm going to take a moment, and I'm going to set each one of these up, and then I want you to pause to see if you can figure out what those inverse functions are. Okay? So step 1 here. And you don't have to write the 1. But step 1 would be to say that this is really x equals y minus 2 squared minus 7. That this is x equals 2 times y cubed plus 1. And that this guy is y equals 2 times the square root of y minus 3. So right now, take a moment. I've just given you that first step, step 1. You want to try step 2, the solving part. So pause right now and see how you do. All right, welcome back, folks. So now I'm going to run through the process of finding the inverse. So in this quadratic scenario, I would add 7. So I'd have x plus 7 equals y minus 2 squared. Then I would have to take the square root to eliminate the squared. So I now have the square root of x plus 7, so I don't need those parentheses anymore. And then I'd have to add 2. So I would have the square root of x plus 7 plus 2 equals y. Officially speaking, that would mean f inverse of x is the square root of x plus 7 plus 2. All right, so there's my first inverse. All right, next one, I would subtract 1. So I've got x minus 1 equals 2 times y cubed. Now I would divide both sides by 2. I'm going to leave this as this like quantity, x minus 1 over 2 equals y cubed. All right, to get rid of the cube power, I would take the cube root. So now I've got the cube root of x minus 1 over 2 equals y. So that means this inverse is the cube root of x minus 1 divided by 2. And that should make sense, because how do I undo a cube? I use a cube root, right? Same thing here. How do I undo a quadratic? A square root, right? Okay, last problem. Oh, I'm so sorry, guys. I hope that didn't totally mess you up. That's an x right there. Now, this problem, there are 2 ways you could approach this, okay? I'm going to go with the most traditional route, okay? Meaning, you're supposed to isolate the radical, so I'm going to divide both sides by 2. So I get x over 2 equals the square root of y minus 3. And then I'm going to square both sides. So that means I get x squared over 4 equals y minus 3, because those are gone. And then I'm going to add 3. So x squared over 4 plus 3 equals y. Now, I want to keep in mind, so our inverse is x squared over 4 plus 3. There are a few ways you could write that answer. Like you could write it as 1/4 of x squared plus 3. You could make the 3 12 over 4 so that you could make it one fraction. All of those are acceptable. The one thing I will comment on is that right here, you could have squared both sides, but a common error is that squaring both sides, people forget to square the 2 to get the 4 that ultimately arrives in the denominator. So just keep in mind, if you wanted to square both sides first, you could, but then you have to make sure you're squaring every part of that side, so including this 2 right here. All right, last thing to talk about, I think, is the horizontal line test. So when you're testing if something is a function, use the vertical line test. So the vertical line test determines if a graph represents a function. Okay, so that'd be like me drawing a line right here, line right there. Nowhere does that graph hit that vertical line more than one place. So the vertical line test determines if you have a function. The horizontal line test determines if your inverse is a function. So like in this case, this is the graph of x cubed. So if I moved this horizontal line anywhere up or down, it would never cross. So it would never cross more than once. So that inverse, the x cubed, is a function. However, the parabola, this graph is of x squared, hits twice. So that means the inverse of a parabola isn't a function. What that means is that when you draw that, it's not going to be identical. There are going to be some limitations, which, if you think about it, for the square root function, the domain, the parent domain, is 0 to infinity. So you know that it's limited, even though the domain of the x squared function, the quadratic, is all real numbers. So that's just a little heads up. That's how you can tell if the inverse is or isn't a function. Okay, so most likely, I think this is going to be the last thing that we talk about. So you can verify functions are inverses using our skill of composition. Okay, so here's the deal. We've already established that inverse functions undo each other. Okay, we've already stated that. Hopefully, you're just sick and tired of hearing that word undo. But what you also should know is that when you evaluate a function for a specific input and then evaluate at the inverse at the output, you should get the original value. Long story short, if you take f and put g in it, and those two things are inverses, you're going to get x. And that would be the same if you took g and then put f of x in it. You'd get x. So I'm going to show you what I mean because I think sometimes the showing is more helpful than anything else. So we're going to test or determine if these two things I have written out are actually inverses. So I'm going to take f of g of x first. So I'm going to put this guy in there. So that's 3 times the quantity of x plus 1 over 3 minus 1. Because this, what's in parentheses, was g, right? So I get 3 divided by 3. Those divide out. So I get x plus 1 minus 1. And I have a positive 1 and a negative 1. So I get x. Now, if I take g of f of x, so that means I take 3x minus 1 and I put it into g, I'm going to have, instead of x, I'm going to have 3x minus 1 plus 1, because x is in the numerator, over 3. So there's nothing other than a 1 in these in front of those parentheses. So I can just drop the parentheses. Negative 1 plus 1, it's just 0, so I really just have 3x divided by 3. 3 divided by 3 is 1, so I really just get x. So yes, these two functions are inverses because when I substitute one into the other and vice versa, I get x both times. All right, try the same thing with the second set of functions I have here for you. Pause for a moment, try it out. All right, welcome back. So let's see. F of g of x equals 8 times the cube root of 2x cubed. So those divide out. So I'm left with 8 times 2x. That is 16x. Not looking promising. G of f of x. That is going to be 8. Oh, wait, sorry. The cube root of 2 times 8x cubed. Like that. Okay, so that is the cube root of 16x cubed. All right, well, the cube root of the x cubed part, that's just going to be x. But the cube root of 16 is 2 cube root 2, because 16 is 2 to the 4th. So like 3 of those 2's can come out of the root, but one of them needs to stay. So see how these are different? So the answer to are these two things inverses would be no. Definite no. All right, folks, and that is the end of our video. Thank you so much for listening. I hope you got a clear understanding of the fact that inverses undo each other, as evidenced on this side, and that if things aren't inverses, then you should get two totally different outputs when you compose your functions. All right, thanks so much for listening. Have a good one.